Hello student, now we'll start the new topics, that is a Bayes theorem. It is just similar to the conditional probability, but in this case we are taking the different events and the condition for that event also. Now let us start. Bayes theorem. This is the direct application of conditional probability. Theorem: if E1, E2, E3 and En are mutually exclusive and exhaustive events with probability of EI is not equals to 0 and I is equals to 1, 2, 3 up to n, then for any arbitrary event A, which is a subset of union of events EI such that probability of A is greater than 0, then we have, that is the probability of EI conditional A is equals to probability of A intersection EI upon P of A. Therefore, probability of EI into probability of A conditional EI, that is the summation upon summation I is equals to 1 to n, probability of A intersection EI. Now proof that we have, that is the capital A is equals to A intersection E1 union A intersection E2 union A intersection E3 up to union A intersection En. That is A intersection E1, A intersection E2 up to A intersection En are mutually exclusive event, and so probability of A is equals to probability of A intersection I union probability of A intersection E2 union probability of A intersection E3 up to union probability of A, that is a union intersection En. Therefore, probability of A is equals to I is equals to 1 to n probability of A intersection EI, and also probability of A intersection EI is equals to probability of A into probability of EI conditional A. Therefore, probability of EI conditional A is equals to probability of A intersection EI upon P of A is equals to probability of EI into probability of A conditional EI upon I is equals to 1 to n probability of A intersection EI. There are three types of possibilities occurrence in the above formula, that is EI, probability of EI, probability of A conditional EI, probability of EI conditional A, the probability occurrence in above formula, that is the probability of EI, where I is equals to 1 to 3 up to n, are such that probability of EI, that is E1 plus probability of E2 plus probability of dash dash, probability of En is equals to 1, because each events are mutually exclusive. The prior probability, since they are known before the conducting experiment, sum of all the events gets a probability is 1. The probability of A conditional EI tell us how likely the event A under the consideration occur given each and every prior probability, they may refer to as likelihood probabilities of the event A. Given event EI has already occurred, the conditional probabilities of EI conditional A are called the posterior probabilities, as they obtained after conducting experiment Bayes' theorem for n is equals to 3 is explained in the following figure. Now see this here. Three events E1, E2, E3, and A is the condition in between. Probability of A is equals to probability of E1 conditional A, that is E1 probability of A conditional E1 upon P of A. For the second, probability of E2 conditional A is equals to probability of E2 probability of A conditional E2, and third one, probability of E3 conditional A, probability of E3 probability of A conditional E3 upon P of A. Now we'll start the exercise. In exercise, you can understand the full concept of the Bayes' theorem. All the problems are easy. There are 3 bags, each containing 100 marble. Bag 1 has 75 red, 25 blue marbles. Bag 2 has 60 red and 40 blue marbles. And bag 3 has 45 red and 55 blue marbles. One of the bags is chosen at random and a marble is picked from the chosen bag. What is the probability that the chosen marble is red? Now see this. Let B1, B2, B3 be the event that bag 1, bag 2, bag 3 are selected. Clearly, probability of B1 is equals to probability of B2 is equals to probability of B2. That is equal chances, which is equals to 1 by 3. R1, R2, R3 be the event that red marble is drawn from bag 1, bag 2, bag 3 respectively. If capital R is the event that a red ball is drawn, then that is a B1, which is the bag B1 intersection R1. It is for the red marble union. And suppose that bag B2 intersection R2, that is a red ball. Again, next is a B3 intersection R3. This is the event that the red ball is drawn. The event that in the bracket are mutually exclusive. Therefore, probability of B1 into probability of R1 conditional B1 plus probability of B2 into probability of R2 conditional B2 plus probability of B3 probability of R3 conditional B3. Now here we will substitute their values. Now probability of R1 conditional B1, that is equals to probability that the red marble is drawn given that the bag B1 is chosen. Therefore, that is equals to 75 upon 100 into. Similarly, probability of R2 conditional B2 is equals to 60 upon 100. And for the third, probability of R3 conditional B2 is equals to 45 upon 100. Therefore, from 1, probability of R is equals to 1 by 3. And 1 by 3 into 75 upon 100 plus 1 by 3 into 60 upon 100 plus 1 by 3 into 40 upon 100. That is equals to 180 upon 300, and which is equals to 3 by 5. This is the, now again, you can say again, there are the 3 bags, each containing the 100 marbles. Bag 1 has a 75 red bag and 25 blue. Bag 2 has a 60 red and 40 blue marbles, and the bag 3 has 45 red and 55 blue marbles. One of the bags is chosen at random and a marble is picked from the chosen bag. What is the probability that the chosen marble is red? Let B1, B2, B3 be the event that the bag B1, B2, B3 are selected clearly. Probability of B1 is equals to probability of B2. Probability of B1 is equals to probability of B2 is equals to probability of B3 is equals to 1 by 3. That is the selection of the bag. Let R1, R2, R3 be the event in that the red marble is drawn from the bag B1, B2, B3 respectively. If capital R is the event that the red ball is drawn, then the capital R is equals to B1 intersection R1 union B2 intersection R2 union B3 intersection R3. The event that the brackets are mutually exclusive events. Therefore, that is the probability of that is equals to B1, probability of B1 into probability of R1 conditional B1, probability of B2 into probability of R2 conditional B2 plus probability of B3 conditional R3 upon B3. This is the formula. Now we'll find out one by one. Probability of R1 when the bag B1 has been done. That is the probability of red marble is drawn given that the bag B1 is chosen, which is the 75 upon 100. In similar way for the second R2 for the bag B2 60 upon 100 and R3 probability of R3 conditional B3 45 upon 100, and therefore the probability of R for the choosing the red ball from each bag is 1 by 3 into 75 upon 100 plus 1 by 3 60 upon 100 plus 1 upon 3 45 upon 100, and you will get the answer, that is a 3 by 5. Now the second problem. A box contains 2 blue and 3 pink balls, and another box contains 4 blue and 5 pink balls. One ball is drawn at random from one of the 2 boxes and it is found to be pink. Find the probability that it was drawn from first, that is the first box, and the second box. Now here E1, the event that the first box is chosen, E2, the event that the second box is chosen. Therefore, the selection of the box E1, E2 are the mutually exclusive and exhaustive. Therefore, probability of E1 is equals to probability of E2 is equals to 1 upon 2. Let capital A the event that the pink ball is drawn. The first box contains 2 blue and 3 pink balls. That is, altogether is a 5 balls. Therefore, probability of A conditional E1 is equals to probability of that the pink marble is drawn, given that the first box is chosen, that is a 3 by 5. Probability of A conditional E1. Similarly, we can probability of A conditional E2 is a 5 by 9, again the pink, and therefore by the Bayes theorem, the required probability of E1 conditional A is equals to probability of E1 conditional A into probability of A conditional E1 upon probability of E1 conditional E1 into probability of A conditional E1 plus probability of E2 conditional probability of A conditional E2 and that's why it is a 1 upon 2 into 3 by 5 plus upon 1 upon 2 into 3 by 5 plus 1 upon 2 into 5 by 9 and hence three by 10 upon 3 by 10 plus 5 by 18 and hence the answer is 3 by 10. After calculation, you can perform this type of the calculation. This is the which is 3 by 10, 55 plus 50, that is a 54 plus 50 upon 180 and that is equal to 3 by 10 upon 104 upon 180, that is nothing but 3 by 10 into 180 upon 104, that is equals to 3 into 9 upon 52, that is a 27 upon 52. Now in second case, that is it is from the second box. Therefore again by the Bayes theorem, the required probability, that is the probability of E2 conditional A is equals to probability of E2 into probability of A conditional E2, that is probability of E1 into probability of A conditional E1 plus probability of E2 into probability of A conditional E2. Now this is the important that we are requiring that in first example, that is we required that is the whatever the bag we required the rate, but in this case we required from the first box, we required from the second box. These are the two different formulas. Now this is from the second box, that is probability of E2, that is 1 upon 2 50%, and next is the probability of A 5 by 9 1 upon 2 3 by 5 plus 1 upon 2 into 5 by 9 and hence these are the two different formulas we are using to all the problems. Normal calculations is here. Now next, again. Now again here we will repeat the problem. A box contains 2 blue, 3 pink balls, and another box contains 4 blue and the 5 pink balls. One ball is drawn at random from one of the two boxes, and it is found to be pink. Find the probability that it was drawn from the first box and the second box. Now in the first problem, that is in first problem there was not the condition that is a bag is chosen first and second or the third. But here we have the condition that it is a chosen. Now therefore the event that the box is a chosen, E2 the event that the box is chosen from the second box is chosen, E1 E2 are the mutually and exhaustive. Therefore probability of E1 is equals to probability of E2 is equals to 1 upon 2. Let capital A be the event that the ball is drawn from the first box. Ball is drawn. The first box contains 2 blue and the 3 pink balls. Altogether is 5 balls. Therefore, probability of A condition E1 is equals to the probability that the pink marble is drawn given that the first box is chosen, and that is equals to probability of A condition E1 is equals to 3 by 5. And similarly, probability of A condition E2, that is 5 by 9. Therefore, by Bayes theorem, the required probability A E1 conditional A is equals to probability of E1 into probability of A conditional E1 upon probability of E1 into probability of A conditional E1 plus probability of A2 into probability of A conditional E2. Substitute the values, you will get the answer. Now, this is the calculation that you can perform. That is required probability is 27 upon 52. Now third problem. There is a working woman in hostel in a town where the 75% are from the neighboring town. The rest all are from the same town. 48% of women who hail from the same town are graduate, and 83% of the women from the neighboring town are also graduate. Find the probability that the woman selected at random is graduate from the same town. Now again, this problem is very important. To understand the problem, you read 2 to 3 times the same problem. Now what is happening here? That is, there are the working women in the hostel where the 75% are from the neighboring town and the rest are from the same town. This is one thing. And what is next? The graduate woman. That is 48% of women who hail from the same town are graduate, and 83% of the women who have come from the neighboring town are also graduate. Now find the probability that a woman selected at random is a graduate from the same town. Therefore, this is very simple again. What is our required formula? Bayes theorem. That is probability of E1 conditional G is equals to probability of E into probability of G conditional E1 upon probability of E1 into probability of G conditional E1 plus probability of E2 into probability of G conditional E2. Now let us start. Now what's happening here? There are the E1, the event that the woman is from the same town, E2, the woman from the neighboring town. These are the two things. Okay. E1 and E2 are mutually and the exhaustive. Therefore, the probability of E1 is equals to is 25%, which are from the same town. They are the 25%. And from the neighboring town, there was the 75, and that is equals to 1 by 4. What about the next? Probability of E2, which is 75, and that is equals to 75 upon 100. That is equals to 3 by 4. This is important. Now, after consideration that is a G, the event that the woman is a graduate. Since 48% of the women who hail from the same town are graduate and 83% from the neighboring town, they are graduate. Therefore, probability of G conditional E1. What is E1? That is, we required in the question, we have asked that find the probability that a woman selected at random is a graduate from the same town. Therefore, we are considering by the Bayes theorem. That is a probability of G conditional E1 is equals to 48 upon 100 and probability of G conditional E2 that is equals to 83 upon 100. These are the graduate person from the neighboring and the same town. Therefore, by the Bayes theorem, we required from the woman from the same town. That is the probability, the graduate woman from the same town. That is the probability of E1 conditional G is equals to probability of E1 into probability of G conditional E1 upon probability of E1 into probability of G conditional E1 plus probability of E2 into probability of G conditional E2. That is 1 by 4 into 48 upon 100. One by 4 into 48 upon 100 upon 1 by 4 into 48 upon 100 plus 3 by 4 into 83 upon 100. Now the calculations. That is 4 into 100, 4 into 100 get cancelled from numerator and denominator. 48 upon 48 plus 3 into 83. That is 48 plus 249. 48 upon 297. That is a 16 upon 99. Therefore, the required probability is a 16 upon 99. Now see the problem. This is same formula is applied here for the problem number 2 and problem number 3. There is a working woman in the hostel in a town. 75% are from the neighboring town. It's clear that from the same town 25%. The rest are from the same town, which is nothing but the 25%. To solve this problem, to understand the problem, you read the problem number of the times, 2-3 times. 48% of the women who hail from the same town are graduate. Clear. 83% of the women who come from the neighboring town are also graduate. Find the probability that the woman selected at random is a graduate from the same town. It's clear, from the same town. Now here we have the event E1, the event that the woman is from the same town. This is our required event. E2, the event that the woman is from the neighboring town. No problem. E1 and E2 are mutually exclusive and they're just events. What about they are happening? That is the probability of E1, which are the 25% from the same town and 75% from the neighboring town. That is a 25 upon 100. 25 upon 100, that is equals to 1 by 4. E2, 75 upon 100, that is equals to 3 by 4. Now what is our required probability? That is a G is the event that, which is G for the graduate. The event that the woman is a graduate. Since the 48% of the women who hail from the same town are a graduate and 83% from the neighboring are the graduate. Therefore, the probability of G conditional E1 is equals to 48 upon 100. Probability of G conditional E2 is equals to 83 upon 100. Therefore, by the Bayes theorem, the required probability of E1 conditional G, we require from the same town. Therefore, that is equals to probability of E into probability of G conditional E1 upon probability of E1 into probability of G conditional E2 plus probability of E2 into probability of G conditional E2. Substitute the values. That is 1 by 4 into 48 upon 100, which are the graduate from the same town. These are the probability of E1 means what? 25%, which is 1 by 4. 1 by 4 upon 1 by 4 into 48 upon 100. And 3 by 4, which are from the neighboring town. And 83%, which are the graduate. And calculations, you will get the answer. To understand this problem, you read the number of the times and then you can understand this problem. That is the required probability is 16 upon 99. Now the fourth problem. If E1 and E2 are equally likely, mutually exclusive and exhaustive events, that is a, now what's happening here? Probability of E1 is equals to probability of E2 is equals to 1 upon 2. And probability of A conditional E1 is equals to 0.2. Probability of A conditional E2 is equals to 0.3. Find probability of E1 conditional A. Again, this is very simple. The same type of the formula. That is the formula. That is the same type of the formula which is we use here. That is for the problem number 2, 3. See this? E1, E2 are equally likely, mutually exhaustive events. Therefore, probability of E1 is equals to probability of E2 is equals to 1 upon 2. Equally likely, therefore 50-50%. It's a given that the probability of A conditional E1 is equals to 0.2. It's a given. Probability of A conditional E2 is equals to 0.3. Therefore, by the Bayes theorem, what we required? That is the probability of E1 conditional A is equals to probability of E1 into probability of A conditional E1 upon probability of E1 into probability of A conditional E1 into plus probability of E2 into probability of A conditional E2. Substitute the values. 1 upon 2 into 0.2 plus 1 upon 2 into 0.2 upon 1 upon 2 into 0.2 plus 1 upon 2 into 0.3. Now perform the calculation, you will get the result. That is 0.2 upon 0.5 and that is equals to 2 by 5. This is our required probability. Answer in the textbook is different. That's all in this manner. If you are agree, then write this. Therefore, probability of E1 conditional is equals to 2 by 5. Again, I will summarize this problem. If E1 and E2 are equally likely, mutually exclusive and the exhaustive events, and probability of A conditional E1 is equals to 0.2, probability of A conditional E2 is equals to 0.3, find. Property of E1 conditionally. E1 and E2 are equally likely, mutually exclusive and the exhaustive events. Property of E1 is equals to property of E2 is equals to 1 upon 2, given that property of A conditional E1 is equals to 0.2 and property of A conditional E2 is equals to 0.3. These are the given. And again by the base theorem, property of A E1 conditionally is equals to property of E1 into property of A conditional E1 upon property of E1 into property of A conditional E1 plus property of E2 into property of A conditional E2. Now substitute the values. That is 1 upon 2 into 0.2 upon 1 upon 2 into 0.2 plus 1 upon 2 into 0.3. We can take their sum. That is 0.2 upon 0.5. That is equals to 2/5. Therefore, required probability, that is the probability of E1 conditional A is equals to 2/5. Now the problem number 5. Jar 1 contains 5 white and 7 black balls. Jar 2 contains 3 white and 12 black balls. A fair coin is flipped. A fair coin is flipped. It is head. A ball is drawn from jar 1, and if it is a tail, a ball is drawn from jar 2. Suppose that this experiment is done and a white ball was drawn from white ball is drawn. What is the probability that this ball was in fact taken from the jar 2? म्हणजे इथे जार सिलेक्ट करण्यासाठी आपण काय करणार आहोत, कॉइन टॉस करणार आहोत. जर हेड जर आला तर फर्स्ट जार अँड द टेल आलं तर सेकंड जार कन्सिडर करणार आहोत. म्हणून हे फक्त त्यामध्ये कॉइनचं कन्सिडरेशन टाकलेलं. Now when we toss the coin, there is equal possibilities of to get the head and tail. Therefore, the required probability will be 1 upon 2. Now see this. Let even the event that the ball is drawn from the jar 1 म्हणजे हेड आलेला असेल त्या कॉइन वरती, आणि E2 the event that the ball is drawn from the second jar म्हणजे कॉइनचा पासून आपल्याला टेल आलेला असेल. A fair coin is tossed. If the head comes, ball is drawn from the first jar. If the tail comes, the ball is drawn from the second jar. म्हणून प्रॉब्लेम सोपा आहे, पण तो नंबर ऑफ द टाइम्स वाचणं आणि तो डायजेस्ट करणं हे फार इम्पॉर्टंट आहे. Now the event of head and the tail are equally likely and mutually exclusive and exhaustive. Therefore, probability of E1 is equals to probability of E2 is equals to 1 upon 2. that is selection of the jar. Now the W, our required probability, that is required event, the event that the white ball is drawn, since the jar 1 has a 5 white and 7 black balls, okay, and together are the 12. Therefore, the probability of W conditional even is equals to probability that the white ball is drawn from the jar 1, that is a 5 by 12, total are 12, 5 are white. Similarly, probability of W conditional E2 is equals to 3 by 15, total are 15, 3 are white, that is equals to 1 by 5, again by the base theorem. Same formula we are using. The required probability, that is probability of E2 conditional W, which is from the second, and we require the white. That is the probability of E2 into probability of W conditional E2 upon probability of E1 into probability of W conditional E1 plus probability of E2 into probability of W conditional E2. Substitute the values 1 upon 2 into 1 by 5, 1 upon 2 into 5 by 12 plus 1 upon 2 into 1 by 5, and you will get the answer. Normal calculations are there. 1 by 5 upon 25 plus 12 upon 60. 1 by 5 into 60 upon 37. That is equals to 12 upon 37. This is the required probability. All the problems are easy. Read the problem number of the times. Same type of the formula are applied there. Now see this again. Jar 1 contains 5 white and the 7 black balls. Jar 2 contains 3 white and the 12 black balls. 3 fair. A fair coin is flipped. If it is head, a ball is drawn from the first jar. If it is tail, it is from the second jar. Suppose that the experiment is done and white ball is drawn. What is the probability that the ball was in fact, it is from the second jar? Therefore, even the event that the ball is drawn from the first jar. E2, the event that the ball is drawn from the second jar. No problem. A fair coin is tossed now. If it is head, the ball is drawn from the first one. If it is tail, it is drawn from the second one. Event that, we require the event that the selection of the jar or the tossing of the coin is equally liked. That is the probability of E1 is equals to probability of E2 is equals to 1 upon 2. जर समजा तिथे हेड असेल टेल असेल, it is equally likely. त्याचप्रमाणे selection of the jar, that is probability of E1 is equals to probability of E2 is equals to 1 upon 2. Now let the W is the event that the white ball is drawn. Since the jar 1 has a 5 white and the 7 black balls, that is a together 12. That is the probability of W, white ball, conditional E1 is equals to probability of that the white ball is drawn from the jar 1, which is 5 by 10, 5 by 12. And similarly, W, white ball is drawn from the second jar, is a 3 by 10, which is equals to 1 upon 5. Therefore, the by-base theorem, the required probability, we required from the second one, that is probability of E2 conditional, the white, that is the probability of E2 into probability of W conditional E2, and substitute the values, then you will get the answer. That is equals to, the required probability is equals to 12 upon 37. Now the next problem, problem number 6. A diagnostic test has a probability 0.95 of giving a positive result when applied to a person suffering from a certain disease, and probability 0.10 giving a false. That is a positive result when applied to non-suffer, it is estimated that 0.5% of the population are suffers. Suppose that the test is now administered to a person about who have no relevant information relating to the disease, apart from the fact that he or she comes from this population. Calculate the probability that gives a positive result. The person is suffer. Given a negative result, the person is non-suffer. Now for that, now I will again repeat the problem. A diagnostic test has probability of 0.95 of giving a positive result when this test is applied to a person suffering from a certain disease, and a probability 0.10 of giving positive result when applied to non-suffer. Again, next thing is that it is estimated that the 0.5% of the population are sufferers. Suppose that the test is administered to a person whom we have no relevant information relating to the disease. Calculate the probability that a given a positive result, a person is sufferer. Given a negative result, the person is a non-sufferer. Therefore, in this case, we have the two events. The first is the event that the person is sufferer, E2 the person is non-sufferer. E1 and E2 are mutually exclusive and the adjunctive events. It is given that the 0.5% of the population are the sufferer. Next, 99.5% of the population are non-sufferer. Yes, these are the population who suffers, and 99.5% of the population is a non-sufferer. Therefore, 0.5 upon 100, that is sufferer. That is person. That we have taken the E1 is equals to the event that the person is sufferer, 0.5 upon 100, and that is equals to 0.005. E2, that is a 99.5 upon 100. These are the non-sufferer. That is equals to 0.995. Now let T the event that a result is positive. Okay. T the result is positive. Since the test has a probability of 0.95 of giving the positive result when a person is sufferer, and 0.1 when the person is a non-sufferer. म्हणजे नॉन सफररला जरी अप्लाय केली तर तो 0.1 दाखवतो. We have probability of t conditional E1 is equals to 0.95. Probability of t conditional E2 is 0.10. These are the important. Now, by the Bayes theorem, the required probability, that is the probability of E1 conditional t is equals to probability of E1 into probability of t conditional E1 upon probability of E1 into probability of t conditional E1 plus probability of E2 into probability of t conditional E2. Now substitute the values. That is a 0.005 into 0.95, 0.005 into 0.95 plus 0.995 into 0.1. After the calculations, you will get the result. For this, to understand this problem, read the number of the times, then you will understand the problem. Therefore, this is the required probability. Now T dash, the event that given result, the person is a non-sufferer. Negative result, negative test, that is a probability of T dash conditional E1 is 1 minus probability of T conditional E1, that is a 1 minus 0.95. That is a person who suffers, but we have given the negative result is a probability of T dash conditional E1 is equals to 0.05. Next, probability of T dash conditional E2 is 1 minus which is 0.9. Therefore, again by the Bayes theorem, the required theorem, that is a probability of E2 conditional T is equals to that is T dash is required there. Here. Now substitute their values. Their multiplication again see. Now see the same problem. Diagnostic test has a probability of 0.95 of the giving the positive result applied to a person suffering from a certain disease, and the probability 0.10 giving a positive result when applied to a non-sufferer. It is estimated that the 0.5% of the population are the sufferer. Suppose that the test is now administered to a person about who have no relevant information relating to the disease. Then calculate the probability that the given a positive result, the person is sufferer, given a negative result when a person is a non-sufferer. Now here again the event that the person is sufferer, E2 the event that the person is a non-sufferer. Now E1 and E2 are mutually exhaustive events. Therefore, it is given that the 0.5% of the population are the sufferer and the 99.5% of the population is a non-sufferer. That is the probability of E1 0.5 upon 100. That is 0.005. Probability of E2 99.5 upon 100, which are the non-sufferer, which is a 0.995. Let T the event that the result is positive. Since the test has a probability of 0.95%, 95 of the giving positive result when the person is sufferer and 0.10 when a person is non-sufferer, we have the probability of T conditional E1 is equal to 0.95 and probability of T conditional E2 is 0.10. Therefore, all we have calculated now by the Bayes theorem. The required probability, that is the probability of E1 conditional T, that is the probability of E1 into probability of T conditional E1 upon probability of E1 into probability of T conditional E1 plus probability of E2 into probability of T conditional E2, that is equals to 0.005 into 0.95 upon 0.005 into 0.95 plus 0.995 into 0.1, and after the calculation you will get 0.00475 upon 0.10425. Now the T dash, the event that the test is a negative. Therefore, probability of T dash conditional E1, that is the 1 minus probability of T1 conditional E1, 1 minus 0.95, that is a negative. Therefore, which is 0.05. Probability of T dash conditional E2, that is 1 minus probability of T conditional E2, and 1 minus 0.1, which is 0.9, again by the Bayes theorem. That is the probability of E2 conditional probability of E2 conditional T dash must be there is equals to this was by mistake. There is not written T dash complement is equals to probability of E2 into probability of T complement conditional E2 upon probability of E1 into probability of T complement conditional E1 plus probability of E2 into probability of T complement conditional E2. Substitute the values and then you will get the required probability. The problem is tough. You have to read the number of the times, then you can understand what type of the consideration is there. Now the problem number 7. A doctor is called to see a sick child. The doctor has prior information that 80% of the sick children in that area have flu, while the other 20% are sick with measles. Assume that there is no other disease in that area. A well-known symptom of measles is rash, from the past record. It is known that chances of having rashes given that sick child is suffering from measles is 0.95. However, occasionally, children with the flu also develop rash whose chances are 0.08. Upon examining the child, the doctors finds a rash. What is the probability that the child is suffering from the measles, which is in Marathi we call the Goa? Now again read the problem number of the times, then you can understand it. Otherwise, it's very complicated to understand. Now let E1 the event that the child has flu, and E2 the child has the measles. It is given that E1 and E2 are again mutually exclusive and exhaustive events. Also, probability of E1 is 0.80%, that is 80 upon 100, which is 4 by 5. Probability of E2 is equals to 20%, 20 upon 100, which is the 1 by 5. Let capital R the event that the child has rash. Since the chances of having the rashes if the child is suffering from measles is 0.95%, and the chances of having the rashes if the child has a flu is 0.08%. 0.08. We have probability of R conditional E2 is equals to 0.95 and probability of R conditional E1 is equals to 0.08. Therefore, by the Bayes theorem, the required probability of E2 conditional R is equals to probability of E2 into probability of R conditional E2 upon probability of E1 into probability of R conditional E1 plus probability of E2 into probability of R conditional E1. Now substitute the value, that is 1 by 5 into 0.95 upon 4 by 5 into 0.08 plus 1 by 5 into 0.95, that is 0.95 upon 0.32 plus 0.95, that is 95 upon 0.95 upon 1.27, that is equals to 95 upon 127. That is the probability of E2 conditional R is equals to. A doctor is called to see a sick child. The doctor has a prior information that 80% of the sick children in that area have the flu. While the other 2% are sick with the measles, assume that there is no other disease in that area. A well-known symptom of the measles is a rash from the past record. It is known that the chances of having the rashes, given that the sick child is suffering from the measles, is 0.95. However, occasionally children with the flu also develop the rash. whose chances are 0.08. Upon examining the child, the doctors finds the rash. What is the probability that the child is suffering from the measles? So again, now see this E1, the event that the child has a flu, E2, the event that the child has measles. It is a given that the E1 and E2 are mutually exclusive and the exhaustive events. Probability of E1 is equals to 0, that is 80%, which is 80 upon 100, that is a 4 by 5. E2, 20%, 20 upon 100, which is 1 upon 5. Let R the event that the child has a rash. Since the chances of having the rash if the child is suffering from the measles is 0.95 and the chances of having the rash if the child has a flu is 0.08. Therefore, we have the probability of R conditional E2 is 0.95 and probability of R conditional E is equals to 0.08. By the base theorem, the required probability, that is the probability of E2 conditional R, is equals to probability of E2 into probability of R conditional E2. That is a probability of E1 into probability of R conditional E1 plus probability of E2 into probability of R conditional E1. That is 1 by 5 into 0.95 upon 4 by 5 into 0.08 plus 1 by 5 into 0.95. That is a 0.95 upon 0.32 plus 0.95. That is a 0.95 upon 1.25. That is a 95 upon 1.20. That is 127. That is therefore the probability of E2 conditional R is equals to 95 upon 125. Again, I am repeating again. To understand this type of the problem, read the problem number of the time, then you can understand this problem. Now the next problem number 8. 2% of the population have a certain blood disease of serious from 10% have in a mild form and 88 do not have it at all. A new blood test is developed. The probability of testing the positive is 9 by 10. If the subject has the serious form, that is 6 upon 10. If the subject has a mild form, and 1 upon 10 if the subject doesn't have the disease. A subject is tested positive. What is the probability that the subject has a serious form of the disease? Now see this again for a problem. That is, 2% of the population have a certain blood disease of a serious form and 10% in a mild form. 88% do not have at all. The total is 100. Okay. A new blood test is developed. The probability of the testing positive is 9 by 10 if the subject has serious, which is the 2%, 6 by 10 if the subject has a mild form, and 1 upon 10 if the test doesn't have the disease. A subject is tested positive. What is the probability that the subject has the serious form of the disease? Okay, 2% serious, 10% mild, 88% do not. What about the test? Test is positive, 9 by 10. for the series form, 6 by 10 mild and 1 upon 10 do not have. Now see this. Now here even the event that person has a serious blood disease, E2 the event that person has mild blood disease, and E3 the event that the person has no blood disease. Okay. Even E2, E3 are mutually exclusive and exhaustive events. It's a given that the probability of E1 is 2%, 2 upon 100, E2 is 10%, and last is probability of E3 is 88%, that is 88 upon 100. Let capital T, which shows the positive test. Now the positive test for the first, since the probability of a testing positive is 9 by 10, if the subject has the serious form, that is 6 upon 10. If the subject has the mild form, that is 1 upon 10. Sorry, 1 upon 10. If the subject does not have the disease, that is for the mild is 6 upon 10. Serious 9 upon 10, mild 6 upon 10, and no 1 upon 10. Therefore, by the Bayes theorem, the required probability of E1 conditional T, which is the serious form, blood disease. Therefore, that is written as like this. You can write and substitute their values: 2 upon 10, 9 upon 10, 2 upon 100, 2 upon 100, sorry, 2 upon 100 into 9 upon 10 upon 2 upon 100 into 9 upon 10 plus 10 upon 100 into 6 upon 10, 88 upon 100 into 1 upon 10, and perform the calculations. That is 10 and 100 to the denominator is a common. Therefore, the calculations you will get 9 upon 83. This is the required probability. Problem, the event E1, the event that the person has serious blood disease, E2 mild, E3 no. E1, E2 are the mutually exclusive and their probability 2%, 10%, 88%. Next, T, the test, has a positive test, is 9 by 10 if the subject has serious, 6 by 10, mild, and 1 upon 10. Those who do not have the disease. That is probability of T conditional E1 is 9 by 10, probability of T conditional E2 6 by 10, probability of T conditional E3 is 1 upon 10. Therefore, by the Bayes theorem, the required probability of E1 conditional T is equals to probability of E1 into probability of T conditional E1 upon probability of E1 into probability of T conditional E1 plus probability of E2 into probability of T conditional E2 plus probability of E3 into probability of T conditional E3. Substitute the values and you will get the answer. Again, to understand the problem, read the number of the time problem, then you will you will understand the concept given in the problem. That is the correct answer is 9 upon 83. Now let's see the next problem. A box contains 3 coins, 2 fair coins and 1 fake. 2-headed coin. A coin is picked randomly from the box and tossed. What is the probability that I will repeat again. A box contains the 3 coins, 2 fair coins and 1 fake 2-headed coins. A coin is picked randomly from the box and tossed. What is the probability that it lands head up? If happens to be head, what is the probability that it is a 2-headed coin? Let E1 the event that first fair coin is selected. E2 the event that second fair coin is selected. E3 the event that 2-headed coin is selected. H the event that the head turns up. Then probability of E1 is equals to probability of E2 is equals to probability of E3 is equals to 1 upon 3. That is probability of H conditional E1 is equals to 1 upon 2. Probability of H conditional E2 is 1 upon 2. Probability of H conditional E3 is equals to 1. Because here we have the 100% probability. Because both sided are the headed. That's why we have taken here 1. Now, the next is head will turn up if any one of, that is E1 intersection H, E2 intersection H, E3 intersection occurs. These events are mutually exclusive. That is probability of H is equals to probability of E1 intersection H plus probability of E2 intersection H plus probability of E3 intersection H. That is equals to probability of E1 into probability of H conditional E1 plus probability of E2 into probability of H conditional E2 plus probability of E3 into probability of H conditional E3. Now substitute the values. That is 1 by 3 into 1 upon 2, 1 by 3 into 1 upon 2 and 1 by 3 into 1. That is the probability of head conditional E3. Both of them have the head. Substitute the values. E1, E2, E3 are the equally likely. Therefore 1 by 6 plus 1 by 6 plus 1 by 3, 2 by 6 plus 1 by 3, that is equals to 2 by 3. B, by the base theorem for the second, that is it happens if 2 be the head, what is the probability that it is the 2-headed coin? Therefore again by the base theorem we will take the 2-headed. Probability of E2 conditional, probability of E3 conditional H, probability of E3 into probability of H conditional E3 upon probability of, see this formula. Now again simplify, substitute the values, that is 1 by 3, 1 by 3 into 1 upon 2 plus 1 by 3 into 1 upon 2 plus 1 by 3 into 1. Therefore, again I will repeat that. To understand the problem, reread the number of the times, then see these solutions. Then you will understand properly. That is equals to 1 upon 2. A box contains 3 coins and the 2 fair coins and 1 fake 2-headed coins. A coin is picked randomly from the box and tossed. What is the probability that it lands up head? And if happens to be head, then what is the probability that it is a 2-headed coin? Now, even the event that the fair coin is selected, E2, event that the second fair coin, and E3, the event that the 2-headed coin is selected, H, the event that the head turns up. Probability of E1 is equals to probability of E2 is equals to probability of E3 is 1 by 3. Again, the probability of H conditional E1 is equals to 1 upon 2, probability of H conditional E2 is equals to 1 upon 2, probability of H conditional E3 is 100%, that is 1, because both of them have the head. Now head will turn off if any one of, that is E1 intersection H, E2 intersection H, E3 intersection H occurs. These events are mutually exclusive. Probability of H is equals to probability of E1 intersection H plus probability of E2 intersection H plus probability of E3 intersection H. And therefore probability of E1 into probability of H probability of H conditional E1 plus probability of E2. This formula we have used in the problem number 1. Probability of E2 into probability of H conditional E2 plus probability of E3 into probability of H conditional E3. Substitute the values 1 by 3 into 1 upon 2 plus 1 by 3 into 1 upon 2 plus 1 by 3 into 1, and you will get the required answer, which is the 2 upon 3. For the next, by the base theorem, here we will apply here the required probability, that is the probability of E3 conditional H, the probability of E3 into probability of H conditional E3 upon probability of E1 into probability of H conditional E1 plus probability of E2 into probability of H conditional E2 plus probability of E3 into probability of H conditional E3. Substitute the values, then you will get 1 upon 2 after the calculation. Now we'll see the next problem. Now the problem number 10. There are 3 social media groups on a mobile, group 1, group 2 and group 3. The probabilities that the group 1, group 2 and group 3 sending the messages on the sports are 2 by 5, 1 upon 2 and 2 by 3 respectively. The probability of opening the message by group 1, group 2 and group 3 are 1 upon 2, 1 by 4 and 1 by 4 respectively. Randomly, one of the message is opened and found a message on sports. What is the probability that the message was from the group 3? Now let E1, E2, E3 be the events that the group 1, group 2 and group 3 open the messages. Probability of E1 is equals to 1 upon 2. Probability of E2 is equals to 1 by 3. Probability of E3 is 1 by 4. E1, E2 are mutually exclusive and the exhaustive. Let M is equals to the event that the message on sports is sent. Probability of M conditional E1, that is the probability that the sports message is sent given that it is from the group 1, that is a 2 by 5. Similarly, probability of M conditional E2 is 1 upon 2. Probability of M conditional E3 is 2 by 5. Therefore, again by the Bayes theorem, that is probability of E3 conditional M is equals to probability of E3 into probability of M conditional E3. Probability of E1 into probability of M conditional E1 plus probability of E2, that is the probability of E2 into probability of M conditional E2 plus probability of E3 into probability of M conditional E3. Substitute the values. Then you will get 1 upon 2, 2 by 5 plus 1 by 4 into 1 upon 2, 1 by 4 into 2 by 3, and see the calculation. 1 by 6 upon 1 by 5 plus 1 by 6. That is equals to 1 by 6 into 120 upon 59. That is a 20 upon 59. Now see this again. There are the 3 social media on a group, on a mobile, group 1, group 2, group 3. The probability that the group 1, group 2 and the group 3 sending the messages on the sports are the 2 by 3, 1 upon 2 and 2 by 3. 2 by 5, 1 upon 2, 2 by 3 respectively. The probability of opening the message by the group 1, group 2, group 3 are 1 upon 2, 1 by 4 and 1 by 4 respectively. Randomly one of the message is opened and found a message on the sports. What is the probability that the message is from the group 3? Again the E1, E2, E3 be the events that the group 1, group 2 and the group 3 open the message. Therefore, probability of E1 is 1 upon 2, probability of E2 is 1 by 4 and probability of E3 is also 1 by 4. E1, E2, E3 are mutually exclusive and the exhaustive. Therefore, let M be the event that the message on the sports is sent. Therefore, probability of M conditional E1, that is the probability of the sports is, that is the probability of M conditional E1, probability that the sports message is sent given that it is from the group 1 is 2 by 5. Similarly, probability of M conditional E2 is 1 upon 2, probability of M conditional E3 is 2 by 3. By the Bayes theorem, the required probability, that is the probability of E3 conditional M, is equals to probability of E3 into probability of M conditional E3 upon probability of E1 into probability of M conditional E1 plus probability of E2 into probability of M conditional E3, E2 plus probability of E3 into probability of M conditional E3. Substitute the values. Therefore, you will get the answer. Now next, problem number 11. Activity. Mr. X goes to office by auto, car and train. The probabilities of him traveling by these modes are 2 by 7, 3 by 7, 2 by 7 respectively. The chances of him being the late to the office are 1 by 4, 1 upon 2, 1 by 4, 1 by 4 respectively. by auto car and the train. On one particular day, he was late to the office. Find the probabilities that he traveled by car. Let A, C and T be the event that Mr. X goes to the office by auto, car and train, respectively. Let capital L be the event that he is late, given that probability of A is 2 by 7, probability of C, that is a car, 3 by 7, probability of T is 2 by 7, which is we have known. Probability of L conditional late by the auto is 1 by 2. Probability of L conditional C 1 by 4. Probability of L conditional T is 1 by 4. That is probability of L is equals to probability of A intersection L plus probability of C intersection L plus probability of T intersection L. Substitute the values. Probability of P. Substitute the values, which is 2 by 7, 1 upon 2, 3 by 7, 1 by 4, 2 by 7, 1 by 4, which is 4 upon 28, 3 upon 28, 2 upon 28, and probability of C conditional L is equals to probability of C intersection L upon probability of L, that is equals to probability of C into probability of L conditional C upon probability of L. Substitute the values, 3 by 7 into 1 by 4 upon 9 by 28. Therefore, probability of C conditional L is equals to 1 upon 3. Again repeat. The Mr. X goes to the office by auto, car and the train. The probability of him travel by these modes are 2 by 7, 3 by 7, 2 by 7 respectively. The chances of him being the late are 1 upon 2, 1 by 4 and 1 by 4. It means that if he go by the auto is 1 upon 2, by car 1 by 4 and by train 1 by 4 respectively, and on one particular day he was late to the office. Find the probability that he was traveled by the car. Now A, C, T are the events that the Mr. X goes to the office by the auto, car and train respectively. Let L be the event that he is late. Now probability of E, auto is 2 by 7, car is 3 by 7 and train is 2 by 7. Now the late probability of L conditional जेव्हा तो ऑटोने जाईल तेव्हा 1 upon 2, कारने जाईल 1 upon 4 and trainने जाईल तेव्हा 1 upon 4. That is probability of L, that's a late. The probability of these are the chances for their late, that is equals to 9 upon 28. Therefore the probability of C conditional L is equals to probability of C intersection L upon P of L. Therefore probability of C into probability of L conditional C upon probability of L, that is we have calculated, which is 9 upon 28. Substitute the values, therefore you will get 1 upon 3 when it travels by the car. And in this way we have completed the base theorem. Now again I will say that to understand this type of all the theory problems, you read the problems number of the times, then see the solution number of the times, then you will understand the concept given in the problem. Now we'll see in the next video. Till then, goodbye.